So I'm going to explain to you some recent work that Carlos and I did, which deals with finding optimal paths and optimal weight distribution in networks using large deviation methods. The idea is to use the dynamics of random walks to explore and to extract information on structural properties of networks. So the structure of the talk is as follows. First, I will present a very brief introduction to something you know very well, which is the statistical mechanics of non-interacting spins, just to set some notation. And then I will explain briefly the idea of the statistical mechanics of trajectories. And this will be still introductory, still background material. And then in the third part, I will start talking about our work about optimal paths and weight distributions. And I will start with the motivation. And then a worked out example. This will be an example where you can see the solution already from looking at a graph, but I will show how you can extract that information. Is sort of obvious to you already with the methods that we use. And then after doing that, we will start seeing some examples that are not so trivial. Still, they are meant to be visually clear in the sense that we illustrate the framework and the ideas. But they are, the ideas will be generally applicable also to larger networks and more complicated problems than those we deal with here. So it's basically a framework to extract that information on optimal paths and optimal weight distributions. And at the end, I will present some conclusions and some ideas for future work, where I expect some of you may perhaps have something to add. And of course, at any time, you can just interrupt me or ask any questions. So first, introduction, statistical mechanics of non-interacting spins. The idea is very simple. We have n Ising spins, and they take values in -1, 1, as you know. So that means you have 2 to the n configurations. Now, if you count the number of configurations with a given magnetization, and I want to make the distinction between capital M, which is the total magnetization, which is an extensive quantity, and small m, which is the magnetization per spin. Okay, so if you count the number of configurations with a given magnetization for a given number of spins, this is the number you get. It's simply simple combinatorics. And if you have a very large number of spins, you know that the dominant contribution has this exponential form, where basically you apply Stirling's approximation to each factorial here and here. And this factor in the exponent, that is, there's a factor of n, and there's a quantity that doesn't depend on the number of spins, which is the entropy. Okay, now, typically, you're not interested in a problem where only entropy considerations are important. You also consider energy. You also consider, for example, that you have energy that fluctuates according to a given beta, given inverse temperature. And in that case, your thermodynamic potential, the thermodynamic potential you're interested in is the free energy. And for that, what you do is you calculate the partition sum or partition function. And if you have a given Hamiltonian, and again, I make the same distinction, you have the extensive Hamiltonian and the energy per spin. If you calculate it, again, I use the same symbol, but in this case, is the degeneracy, the number of configurations with a given energy and number of spins, again, takes this form. Now, for large n, you can use the fact that this takes this large deviation form and apply a saddle point approximation. And the dominant contribution is like this, where E star is the energy that maximizes this quantity. Now, this quantity is not the quantity that is commonly used in thermodynamics, but after a slight rearrangement of the exponent, you find that you take minus beta outside and you write it like this, and this is actually the free energy. Okay, of course, we are not, in the way we are computing it here, Boltzmann factors and so on do not appear. This is the look of those expressions in standard thermodynamics. So finally, you have a certain competition between energy and entropy for different temperatures. So let's see that, for example, in the case of the presence of a uniform field. So in that case, the energy is minus the magnetization. Let's assume that the uniform film has a magnitude 1. And in that case, the probability of a given magnetization takes this form. Again, this is the degeneracy, the number of states with a given magnetization, which in this case is the number of states with a given energy. And this is the Boltzmann factor. And the probability concentrates around the free energy minimum, which takes this well-known form. And for very large temperatures, beta going to 0, the entropy dominates, and basically the probability concentrates around the entropy maximum, and the entropy takes this form. This is the entropy I calculated before. And this, by the way, this green line here is what you get when you perform a quadratic approximation around the maximum. So this would be your central limit approximation to the actual large deviation function. So it gives you the quadratic fluctuations of the large deviation function around the maximum, but there's more to the entropy than just the Gaussian fluctuations, as you can see. And if you don't have such high temperature, but the temperature becomes more reasonable, then you start having also energy coming into play. And in that case, the energy, for example, the free energy, sorry, takes this form. And if you change, for example, for beta 1/2, the minimum is no longer at the magnitude at the magnetization 0, which is your maximum of the entropy, but starts moving towards +1, which is what you get for temperature 0, strictly speaking. And so these are simple ideas that you're all familiar with. And now what I'm going to explain is how these ideas change when you move to a statistical mechanics, not of configurations, but of trajectories. So in that case, you have probability distributions of, before was static observables, now it's dynamic observables. And before, the probability distributions were distributions over configurations, now it's over trajectories, sometimes called histories. So you have a certain configuration that is changing across time, and at the end you want to study the statistics of observables that are integrated across this whole trajectory. So before, the large deviation results were especially relevant for sufficiently large n, and in thermodynamics one deals with the thermodynamic limit, n going to infinity. Here in dynamic, in the statistical mechanics of trajectories, the large parameter is the time, is the observation time, the duration of the trajectory. Okay, in some problems also the number of particles or whatever it is also that limit is also taken, but it won't be the case in what we will explain later on. So in our networks, the number of nodes, which is capital N, will be finite, but the observation times will always be very large. And the statistics of such observables will be studied using, instead of thermodynamic potentials, generalized free energies, what I call large deviation functions, or dynamic large deviation functions. So in the limit n going to infinity, or time going to infinity, there are non-analyticities which correspond to phase transitions. And this analogy has been exploited during the last few decades. There's a lot of work done on this. Actually, there are some people in the audience that have done a lot on this stuff. And the basic idea, taking back what we were doing about non-interacting spins, but now referring to general statistical mechanics systems, is that we have a number of configurations for a fixed energy and number of particles, and that takes this large deviation form. And in the case of dynamics, we have the number of trajectories for a fixed time-extensive observable and time. And remember that n and t take a similar role in these two contexts. And for the observable, again, I use this trick of distinguishing between the capital A, which is the time-integrated observable, which is time-extensive, and small a, which is the let's say the amount of change in A per unit time, so to say, the contribution to A per unit time. And in that case, we will see also that we have that the number of trajectories acquires this large deviation form where the big parameter is not n, is time. And as long as a finite limit exists, there's a limit here, a function here that you can define by taking the logarithm and divided by time and taking the limit when t goes to infinity. The choice of the observable depends on physical insight and on your problem at hand. It's not, as far as I understand, it's not as universal as the case of thermodynamics, where you know it's the energy and the parameters that enter the Hamiltonian. Here, you have to, it depends on the specific problem. For example, if you have a system in contact with two particle reservoirs, it makes sense to consider the particle current as your observable. So when, in the canonical ensemble, when the energy fluctuates, we know that we have this partition function that acquires this large deviation form with the free energy here. And when the temperature is higher, is lower, sorry, when beta is higher, we know that high energies are suppressed in the system. So in a similar way, when we have dynamics, we have that we have ensembles where the observable can fluctuate. And there is a conjugate parameter which plays the role of the inverse temperature, which is in the most general cases usually called S. We will see there are several ensembles actually. And so we consider that, so before we consider the microcanonical situation where A was fixed and time was fixed, now A can fluctuate and there's a conjugate parameter, which we call S, and the time is fixed as well. And this is called the S ensemble. And when the parameter is large, high values of the observable are less likely. So in that way is analogous. And when S is strictly zero, we have the typical dynamics. We have the natural dynamics of the system. But when we are changing the value of S, we are changing the dynamics to more atypical dynamics, to other, let's say, other statistics of the observables of interest. And unlike beta here S in principle can take positive or negative values. And again, phase transitions are non-analyticities of, in this case, the free energy, in this case, this function, which is called the scale cumulant generating function. And both are cumulant generating functions, in one case of the energy, in the other case of the observable of interest. So in both cases, we have extremum principles. So in equilibrium statistical mechanics, as the number of particles or spins becomes very large, we know that this entropy, actually, number of configurations with a given energy concentrates around the maximum, sorry, the entropy is this, concentrates around the maximum of the entropy, this number of configurations with a given energy. And this kind of Boltzmann factor that appears, this kind of sums, terms that you sum in the partition function, concentrate around the minimum of this quantity, which is the free energy. Now, similarly in dynamics, the number of trajectories with a given observable value for a given duration concentrates around the maximum of this quantity, which is called a rate function, which is like a dynamic entropy. And the terms in the partition sum concentrate around the maximum of this other quantity, which is called the scale cumulant generating function, which is, as I said, a dynamic free energy. Well, and this is a technical issue. These Legendre functional transforms become Legendre transforms, the usual ones, when the function is differentiable and convex, but also when there are non-convexities or non-analyticities. Things are also interesting because they may be related to phase transitions, metastability, or sometimes ensemble inequivalence. For example, people that study long-range interacting systems find that different statistical ensembles are not equivalent, and this is related to this kind of non-convexities of these large deviation functions. And as in the case of equilibrium statistical mechanics, there are static ensembles like the microcanonical ensemble, the canonical ensemble, or the grand canonical, where both E and N fluctuate. And when when one of these quantities fluctuates, one of these extensive quantities fluctuates, there's a conjugate parameter that is fixed, in this case the temperature, in this case the chemical potential. And these conjugate quantities are physically accessible, are experimentally accessible. In the case of dynamics, we also have several ensembles. Actually, I won't explain it in detail because it gets very technical and takes a lot of time. But in the study that I will discuss, we use several different ensembles depending on the problem at hand. So we can talk about that perhaps at the end. But just for you to know that you can also propose different ensembles, like for example a dynamical microcanonical ensemble where both the observable value and time are fixed. The S ensemble was, where, as I said, the observable fluctuates and there's a fixed conjugate parameter and the time is also fixed. There's also the X ensemble where the observable is fixed but the time of the trajectory fluctuates. So you consider trajectories that go on and on until the observable takes a specific value, but the duration of the trajectory can be different on different realizations. And there are also ensembles where you have several observables. For example, the SS ensemble, where you have, instead of one fluctuating observable, two fluctuating observables, or the SX ensemble, where you have one fluctuating observable and the time is also fluctuating, whereas there's another one that is fixed. Okay, and we use all of them actually in the results I showed later on, because they are best adapted to different problems, to different situations. So when a time-extensive quantity fluctuates, there's a fixed conjugate tilting parameter, is sometimes called, or tilting field, S, X, and so on, which play the role of beta, mu, and so on in thermodynamics, but in this case, they are not experimentally accessible. Having said that, we'll see that they reveal interesting information and can lead to proposing new dynamics where you actually achieve those atypical values, atypical fluctuations of the observables. And that is part of what we will do. Okay, so the motivation of our work, this was just an introduction, a 20-minute introduction. I know it's long, but I think after this, everything will be relatively easy to follow. So the motivation is that we want to study shortest paths because they are one of the main objects of interest in network science. They are very important in theory, they are very important in applications, and also there are many measures that are based on them. For example, the closeness, the efficiency, the betweenness, centrality, several measures that are used to quantify properties of different nodes in a network are based on how many shortest paths go across them and so on. And of course, in applications, you can think about transportation networks, for example. Obviously, it's very important to know what are the shortest paths, how many of them are there, and so on. So what we do is we generalize the idea of shortest or other optimal paths in two ways. On the one hand, we choose them to sustain a prescribed mean value or fluctuations of a given path observable. Path observables are the observables A I mentioned before, so time-integrated observables, in the presence of one or several constraints. And we will see that actually the goal that we want to achieve and the constraints that we want to impose on it are very much related. They're simply connected with different dynamic observables. Okay, so for example, questions that we would like to ask and we're able to ask with our framework. What are the paths that join a source node and a target node, minimizing a given cost function without passing through another node more than 1/3 of the times that the target is reached? That is one possible example. And also we perform analogous generalizations for link weight distributions. So this is related to the fact that sometimes you have a network that you have some connections, some adjacency matrix, but you may want to study not the pattern of connections, but also consider the strength of the connections or the correlations among the different units, whatever that means. You want to replace the binary adjacency matrix by an adjacency matrix where the links are real numbers that quantify somehow how strongly are different elements connected. And for that, we can use this framework. And if we take a given binary adjacency matrix, which just tell us what is the basic graph, what is the basic structure of links connecting nodes in the system, we can find a corresponding weighted network that is optimized to sustain a given flow without exceeding a bound on the activity of some links, for example. So we can say how can we maximize the amount of current that reaches that node without passing too frequently through these links here, because I know I don't want to overuse them, because I know that if I don't put any restrictions, perhaps I'm all the time going across that part of the network, so I want to avoid that. So to do that, we study ensembles of trajectories of random walks. Is the idea I mentioned before, but particularized to the case of random walks. And a trajectory of a random walk is simply a sequence of nodes that are visited starting from I0 to I1, I2, up to IT. And here, this coincides, the index coincides with the duration of the trajectory because we consider discrete time random walks. Perhaps at the end, if someone is interested, I can clarify why we use discrete time random walks. They are best adapted to the problem we want to study, that continuous random walks in some sense. So we have this ensemble of trajectories, and of course, each trajectory has an associated probability, and path observables are time-integrated observables where each of these transitions adds something to them. So you have something that is increasing over time, if it's always positive, otherwise it could decrease also. But what I mean is that for each given transition, there's one element that adds something to the observable. Actually, in full generality, this could be, in many cases, could be 0, in some cases could be 1, or it could be any other number depending on the problem. It just means that you add something to the observable as the particle goes around moving, as a random walker moves on the network. So this, of course, has also a probability distribution, and the probability distribution you can calculate from the probability of the trajectories, and it also acquires this kind of large deviation form. This is the rate function, and this is the observable per unit time. And the reason it acquires this large deviation form in the problems we are studying can be related to the Perron-Frobenius theorem of the transition matrix of the random walk. Okay, so what we do, this is of course just what you get with the natural dynamics, when you let the random walk with some transition matrix evolve, and you find a given probability distribution of the observable. But you can also bias the probabilities using different tilting parameters. As we said, it's like we have like this E minus S to A, this kind of Boltzmann factor that is changing, is biasing the distribution towards smaller or larger values of the observable. And set here is a partition function, is just a normalizing factor. So the partition function also takes a large deviation form, like this, with a dynamic free energy theta of S. And from that dynamic free energy, you can find the cumulants, the statistics of the observable of interest. So, for example, the average value is just, you can just obtain from the first derivative of the scale cumulative generating function, and the fluctuations you can obtain from the second derivative. We will be mostly interested in those, but of course, there's no reason to stop there. You can go up to third order cumulants or fourth order cumulants if it's interesting for your problem. So these theta of S can be obtained by diagonalizing what is called a tilted operator. So it turns out that when you perform this tilting on the probabilities, you can see the dynamics as given by another operator, which is not the original transition matrix of your random walk, but it has somehow been varied by this parameter S. And from that, you can actually extract, in all these different ensembles that I mentioned, in all cases, you can extract the scale cumulative generating function from which you can obtain the statistics of the observable. By the way, when you have several parameters, like in the SS ensemble that I mentioned, there could be an A1 and A2. With these derivatives of the scale cumulative generating function, then you have two parameters. So when you take the cross derivatives of two corresponding to two parameters, you get, for example, the correlations. And yeah, I want to say that this tilted operator is useful to extract that, but it's not a stochastic operator, in the sense that probabilities don't add up to 1. You cannot consider it to be a proper stochastic operator. So it's just some operator that you use to extract that information, that large deviation function. And the tilting parameters in the problem are chosen, or tilted operator that you use to extract the statistics are chosen to yield some statistics. So you explore the range of statistics that you have, and you say, okay, I want to find this value of S because I want to have this, for example, this value of the fluctuations of the observable. And after that, after doing that, what one does is, and this is a kind of recent development that has been used for the past 10 years or so, and Carlos has worked on this a lot, is the use of the dupe transform, which basically is a set of rules, is a kind of linear algebraic transformation of your transition matrix that gives you a matrix that has the same statistics that you found for a tilted operator, but it's a proper stochastic operator. So you can run dynamics on it, it conserves probability, and everything you expect from a stochastic process is there. Okay, so let's see one example of what we are doing. So I worked out an example of how to find generalized optimal paths and weight distributions. This is the example I told you that it will be extremely simple. You can see what the solution is going to be, and that's the idea, just to explain it. So we're going to consider one type of random walk, which is called the maximal entropy random walk. I don't want to explain it in detail because it's a modification of a random walk where basically the transition rates depend on the eigenvectors and eigenvalues of the adjacency matrix of the graph. But the property of the random walk that justifies our consideration of it is that the maximal entropy random walk is the random walk for which all trajectories of a given length, of a given number of steps, are connecting two nodes. So starting from a given node S source to a given node T target, all trajectories of the same number of steps have the same probability in this random walk, which is something that doesn't happen with the standard random walks that you use on networks, where basically transition rates are 1 divided by all the different neighbors that you can reach from a given node. Okay, in this case, if you do that, you have paths of the same length joining two nodes that have different probabilities. With the maximal entropy random walk, they have the same probability, and you want to have that because we want all the paths to be equiprobable, of the same distance, to be equiprobable to start with. So with our tilting, we can actually highlight those paths that we want to find. So we will see that is like the most fair initial condition on which we can then add the tilting and the loop transform to extract that information. So the kind of system we study is this very simple ring with a shortcut. So that means that the random walker is starting from the red node and is going there. It just has one possibility, going along the cycle, except when it comes here, it has two possible choices. Either it continues or it takes this shortcut. And these have assigned probabilities that depend on the maximum entropy random walk. It's slightly different from 1/2, but not too different from 1/2 in the case of this network. And the random walker is doing this, sometimes going this way, sometimes going this way. And that's what we are doing. So we consider two possible paths of length 7 and 12, which are the shortcut or the path around the cycle. And we consider m cyclic walks starting at the red node and coming back at the red node again. And of course, they have a certain probability, which is basically the probability that you have when you are here of moving to the right or continuing along the cycle, along the ring. So the probability distribution of the fraction, so you repeat this random walk many times, and the probability distribution of the fraction of walks of a given length of the two possibilities has a binomial, the fraction, yeah, the walks have a length LP or LQ. So the fraction of walks that have a length LP has a binomial distribution, which by Stirling's approximation acquires this large deviation form. And this large deviation form has a rate function, which is the Kullback-Leibler divergence of a Bernoulli trial with probability P and a Bernoulli trial with the fraction of walks that take that length. Okay, so this is minimized for when NP equals P, so that's the highest probability. It's basically the idea of the law of large numbers. So we focus on the walk length as our observable, which by a change of variables also has a large deviation form. So the walk length is simply the fraction of walks with a length P multiplied by that length, and the rest multiplied by the other length. So we change variables here, and we also have a large deviation form, which I'm not showing here, but is essentially this with a change of variables. And now what we do is we bias it. So this is what we get if we don't do anything. Okay, we just run the random walk for sometimes, and then the fraction of random walks or the average length of the random walk is given by some probability distribution. Now we're going to bias the distribution of the walk using the tilting parameter x. And here it's called x because actually the length of the random walk is related to the duration of the trajectory. So it's like this x ensemble that I mentioned, where some observable, which is the number of times you go back to the red node, is fixed, but the duration of the trajectory is changing. It changes from one trajectory to another. So okay, so we bias the distribution, and it takes this large deviation form where the scale cumulative function, the x ensemble, which we denote like this, takes this value. And in this case, everything's so simple that it can be calculated explicitly. And what we find is the following. This is the black curve is a scale cumulative generating function. And we said that the first derivative gives us the average length, and the second derivative, the fluctuations, the scale fluctuations, actually. Okay, we represent them like this. Then we can see what are the different possibilities that we have. And in this case, everything is very simple, so we know what we're going to get. When x gets very large, cycles are suppressed, and we get the lowest possible value, which is 7, which corresponds to the shortcut. Basically, in that situation, for example, if we take x equals 1.5, we just have this kind of motion. And if, on the other hand, x is very small, then we have the opposite. It goes along the cycle, okay, the longest possible trajectory. Now we can set ourselves, for example, at the peak here. We say, okay, we want to maximize the fluctuations. Where do we maximize the fluctuation for this value of x? Okay, let's see what we get for that value of x. If we see what we get is exactly what you expect. It is the same cycle we had, but now the probabilities of going along the ring or taking the shortcut are exactly 1/2. Okay, that is the situation where the fluctuations are maximized. So from the derivatives of the energy, this free energy, we have found the cumulants of the walk length, and then choosing the parameter, we can we can see where we can set ourselves. We want to find ourselves here, what kind of statistics we want, and then applying the dupe transform, which is used to recover these transition rates, actually. Well, these are probability fluxes, are transition rates multiplied by the stationary probability distribution. But anyway, this is the dynamics that we get. We can recover a transition matrix that has that statistics. Okay, the idea is very simple, and with the dupe transform, we find the paths that extremize the walk length or maximizes fluctuations, for example, like this and here. Of course, in this case, there's no need to do that. We know how to do that only by looking at the graph, because it's extremely simple. When it gets much more complicated, this idea can unveil information that is not obvious at all just from looking at the graph. So this is what we are going to see next, is some results where the networks are not as simple. They are not so easy to see, but still everything is very easy to check. You just want to illustrate the framework, okay? If one uses a network which is much larger with much more complicated structure, you will get some results that will be useful to your problem, but we won't gain any insight from seeing them here, because we just have to believe the result. So here the idea is to present some results where you can actually see that everything makes sense. So we consider optimal paths on a random graph, and the random graph has this form in this example, and we consider two observables. On the one hand, we have, this is maximal entropy random walk that I mentioned before. This is dynamics, and we have one observable is the path length, is the length of a trajectory that starts from node 1 and reaches node 20. And we put this on purpose, so when you reach 20, you start all over again. Okay, this can, in an application, this will be either part of your network, or this might be something that you put there by hand to make sure that you calculate several. You put it in your analysis just to make sure that you restart the process when it reaches the end. And apart from the path length joining these two nodes, 1 and 20, we also consider the activity of node 15. We consider node 15 to be an obstacle in quotes, because it's not really a node that we want to avoid. We just want to modulate how much we want to go through it. Okay, so it will be an obstacle when we want to avoid it altogether, but sometimes we will say, okay, we just want to go through it one time out of 5 random walks. Okay, so if we vary the conjugate parameters to these two observables, which are L and K, the conjugate parameters are called X and S, we can explore, in this case, the average value of the two observables as a function of the tilting parameter values. And we have these two color maps where you have the different values that it can take. And the first thing that it looks quite strange is this gray area here. So what is this? So this is an area where we have a divergence. And the divergence is not a numerical thing. You can see mathematically that in the series that you're summing is non-converging when you reach some value here. It's related to eigenvalue of the random walk transition matrix. So it also is related to a particular network you consider. And in this case, let's first see what happens there, because it's the strangest thing of all. So we set ourselves at these values. You see this green star. For this value of S and X, we explore both the length and the activity of node 15, which means how frequently are you going through node 15 every time you go back to node 1. And what we find is that in both cases, it's very large. And if you study the dupe transform, these green lines, this corresponds to the green point, so this will be the green arrows here. The green arrows are just telling you that for that value, you're basically jumping from node 15 to a neighbor and back. And that's all you're doing. And why is that happening? Because you're putting a very large negative tilting of the activity. So basically, you want to have a very large activity. And when you exceed a certain value, the particle does not reach node 1 anymore. It's basically, when you get to the divergence, it just means your condition is having such a large activity that the particle is localized here. Now, less extreme circumstances, for example, let's consider this red point here. This gives you the lowest possible value of L of the path length, which is 4. And this corresponds to an activity in this area, which is 1. So if you apply the dupe transform and you see what kind of trajectories you have there, you have these trajectories that are shown here, these red arrows. And this is what you would expect is the shortest possible path in the network, which in this case, you can easily calculate by other means because it's a very, very small network. And it takes just 4 I mean, its length is 4 because you just have 4 nodes here, and it goes back and so on. And as the shortest path happens to go through node 15, in that case, the activity is 1. Every time you reach node 1, I mean, you start from node 1 and you come back, you have gone once through node 15. Now, less trivial cases than this, for example, is when you avoid node 15. You're in this situation, then you have a length that is 5 instead of 4, and you have an activity which is 0. And you see what is happening there. You have extracted the second shortest paths that do not go across node 15. So actually, if you use one of the standard algorithms like Dijkstra algorithm or any other algorithm for finding paths, you find that there are 5 paths that are of length 5, and of them, there are 2 of them, that go through node 15. Those you're avoiding here by having a positive S. You're avoiding going through that. And basically what you have here is a combination of the 3 other paths of length 15 that do not go through that node. Okay, all with the same probability. If you compute the probability, is 1/3 for each of them. And now, one more interesting case. What if we want to find the shortest possible path that goes through node 15 a given fraction of times? Not just it avoids it altogether or it goes through it all the time, because that's what you get for the shortest possible paths if you don't do anything else, if you just condition the path length. What if you want to do something more sophisticated? For example, you can take the values of the pairs of S and X that guarantee that the activity is, for example, 1/3. That means 1/3 of the times you go in across the network, you're passing through node 15. If you compute that, this corresponds to this straight line. Okay, so this is like the contour line for 1/3 here on this plot. By the way, the points S and X here and here are completely equivalent. It's simply that this corresponds to one observable, this is the other, but the independent variables are the same. So this straight line corresponds to this contour line, and if you go along it, there's a point where basically the path length saturates. It reaches its lowest possible value, and from that point onwards, it doesn't change much. So we just choose some value that is at the beginning of that saturation. So this will be the shortest possible path that corresponds to an activity of 1/3. And if you apply the Duke transform and you see what you get this combination of paths where basically you have one probability, which is 1/3 of taking the shortest path, which goes across node 15, and the other 2/3 are equally distributed on the second shortest paths that do not go across node 15. Because remember, I told you there are some second shortest paths that do go through node 15. So this is what you get. And of course, this is still a simple case, but this is something that you need some analysis to discover. And here, it comes out immediately. And now you could consider much more difficult situations, like, for example, increase the frequency here, decrease the frequency here, avoid this node altogether, and so on and so forth, combining more observables. Okay. And finally, the last example I want to discuss is a spatial network. A spatial network is the example we consider is a disordered lattice. It's a lattice with some noise in the node positions, and it's a spatial network because, unlike in the previous exercises, here each node occupies some point in space. It has some x and y coordinates, and we take that into consideration in the observables. The observables are going to be, so for that we use the standard random walk, a standard network random walk, because technical reasons, again, because of some technical reasons. The horizontal global current is going to be one of the observables. That means how much you're advancing towards the right as you jump. And the other observable is going to be JL, which is the current across the red nodes here. In the horizontal global current, we take into account the coordinates of the x coordinate of the node that you reach minus the x coordinate of the node from which you came. And in the local current, you just take into account if you're going to the right or to the left. Because basically what we want to do is to go how much we can, for example, maximize the current, avoiding to some extent or completely avoiding the nodes here. So again, we have 2 parameters here. This is the SS ensemble because the 2 currents are fluctuating, and we have these 2 parameters. This is conjugate to the global current. This is conjugate to the local current, and what we get is this apparently complicated phase diagram, and where, by the way, if here there's some noise in the node position, if you have a completely regular graph, just a lattice, what you would have is there's a symmetry. If you change the signs of two tilting parameters, basically you get the same currents with a minus sign. Okay, so there's a kind of symmetry, reflection symmetry across this line over here. Here you don't have that exactly because there's some noise in the coordinates. And again, we do the same thing. We look at specific points that give us some values of the observables of interest, and for the loop transform, we find what are the trajectories, what are the dynamics that is sustaining that kind of statistics of the observables. So, for example, in one case, we can consider first we consider this cyan star. And for this, the conditioning on the local current is 0. That means we don't do anything to the local current. We just have the natural value. But we condition the global current. And that means we want, and this is negative, so it leads to larger values of the local current, of the global current that you would have in the natural dynamics. So if you do that, you get these cyan arrows that are basically moving to the right. And they happen to be, just because of the structure of the lattice, they happen to go across this red slit, across these red nodes. Now, if you increase a little bit the conditioning on the local current, you get this blue point where you're basically saying, I don't want to have, you are decreasing the value of the local current. You have a positive conditioning, which means you're decreasing the average value of the local current. And when you do that, you have trajectories that are avoiding the red nodes here to some extent. Okay, you see that these dark blue arrows appear at places where you didn't have any cyan arrows before. Basically, it's because they are also considering trajectories that do not move so fast to the right, but have the advantage of avoiding these nodes and therefore decreasing the local current. And when you get to very large values of the local tilting parameter S, you get to this blue triangle here, or this yellow triangle here, which extends here and here. And this is what you get ultimately when you condition here. And this is because when the local current is what matters, you have such large condition and you're conditioning on positive or negative local current. Basically, what you get is these kind of vortices around the extrema, the endpoints of the slit here, of the red nodes. Okay, because this is the way that you can actually increase your local current the fastest, or here in the opposite situation. Again, this corresponds to dark arrows to the dark square and dark green square, and the light green arrows to the light green triangle. So in this case, you're decreasing the current, the local current a lot, because SL is positive. So that's why you get this counterclockwise motion. And in this case, you're increasing it a lot because SL is negative and very large in absolute value, and that's why it's moving in this direction. And okay, so some conclusions about this. We have shown how to find generalized optimal paths and weight distributions by application of large deviations. So first, we use some parameters to tilt the dynamics in such a way that we get some statistics of observables that we are interested in, and then we use the loop transform to extract the information on the transitions that actually realize those unlikely values in the natural dynamics. As far as we are aware, some of these problems are outside the reach of standard graph theoretical approaches. For example, the idea that you can fix the value of one observable when we said the activity is 1/3, and you're moving the value, the tilting parameter of the other observable to guarantee that the path is as short as possible, going through one node 1/3 of the times, is, as far as we know, not easy to achieve with the standard algorithms that people use when they study shortest paths. And the problem of optimal weight distributions, which is the problem that we studied here in the case of flow on a spatial network, is even less studied than the other. Okay, so probably it's even less likely that there's something similar, but we cannot be 100% sure. And the possibility of combining several observables and constraints results in a versatile approach of wide applicability. At least that's what we hope. And the statistical is a statistical approach, but many people in the complex systems community, when they hear statistical approach, they think that you basically are saying that your results are valid for an ensemble of networks. So for all the networks that are distributed according to a Barabasi-Albert distribution or something like that. Now here, it's a statistical approach for the dynamics, for the random walk, but the random walk is a tool to unveil a structural information. And that structural information is basically that of a particular network. So it can be a network coming from an application, it can be a realization of a given ensemble and so on, but doesn't have to have any simplicity properties or any theoretical description that is not an Erdos-Renyi graph or anything like that. It can be as complicated as you want. And this is, we illustrated with simple examples, but larger networks, which can be directed or weighted, or also contain spatial information, can be analyzed. And some people asked me previously when I presented this work in some conferences about the computational complexity. The computational complexity is that of the algorithm used to compute the largest eigenvalue and associated eigenvectors of a sparse matrix. So in general, it doesn't take long. But again, if you have specific purpose algorithms to find shortest paths, typically they are optimized to be faster, but they are less flexible in the sense that you cannot combine constraints as easily as we do here. So, and some ideas for future work, I would like to precisely about this thing I was mentioning about graph theoretical algorithms to find shortest paths. We would like to have a precise clarification of what problems lie outside the reach of network optimization algorithms that we can do. As far as we know, as I said, there are some problems that we study that are not at all easy to find with those other methods, but the literature is huge. And it spans from theoretical computer science to applied mathematics, statistical physics. Many people study specifically for transportation networks, for example. So one cannot be 100% sure that perhaps all the different points that we extract could be extracted, by other means, and perhaps what we are just providing is an encompass and viewpoint of all these possibilities in the phase diagrams that we are presenting. We don't know about that. We are not sure about that. We'd like to talk to experts on network optimization about that. Then I would like to see if we can use this in the situation of dissipative quantum walks. So Carlos has done some work on large deviations on open quantum systems, and there's the natural generalization of random walks to quantum mechanics, which is dissipative quantum walks. So there's this idea that perhaps something along those lines could be done. We also would like to see if there's a possibility to apply this in biological applications, for example, drug delivery, and also in transportation networks. I've been talking to some people that do that, that work on air traffic optimization using optimization methods. And there's also another idea that is the possibility of using this approach to study networks of many-body configurations. So, for example, optimizing the frequency of visits of given configurations by tuning the transition rates or somehow jump operators or whatever it is, depending on the specific problem, in many-body systems. And, of course, there might be others that we are overlooking at the moment. So if anyone has any ideas, please get in touch with us. And that's it. Thank you very much. This work has been published recently, a couple of weeks ago. So if anyone is interested, you can have the reference here.